All right, today we are going to look at implicit differentiation. But before we can talk about that, we need to really know what the word implicit means. So you looked at this a little bit in pre-calc last year, and it was just kind of touching on the surface. But I want you to think about if your parents say to you, or if they say, I explicitly told you to take out the trash. And this is kind of my age-old example. If someone explicitly tells you to do something, it means that they are telling you the most direct way possible. And so there's no confusion. If someone says something to you implicitly, it means that they're telling it to you in a more convoluted way, that things are kind of mixed up and you may not get the point exactly. And that's the same thing with an implicit versus an explicit equation. And explicit equations are basically all the types of equations we've been dealing with thus far. So an explicit equation is going to be of the form y equals. So we may have something like y equals 1 over x. That's an explicit equation because we are writing this equation explicitly in terms of x. We could have y equals plus or minus the square root of 1 subtract x squared. These are all explicit equations. So this is what we've been dealing with so far. We take the derivative of this side with respect to x, and we get our solution out. What we're going to be looking at now are implicitly defined curves or implicitly defined functions. Oops. And like I said, this means that we're no longer going to have a y equals. Everything's going to kind of be messed up a little bit. So we're going to have x and y together on the same side of the equation. So for example, we could write this equation over here, y equals 1 over x. That could also be represented implicitly as xy equals 1. And we could take the derivative of this using our the notes that we'll take today on how to take a derivative implicitly. This equation right here, if we were to kind of break this down and write it implicitly, would be x squared plus y squared equal to 1. That's the equation of a circle, specifically the unit circle. And so the equation for a circle is an implicit equation because x and y are on the same side of the equation. So now if we had something like this, x squared subtract 2y cubed plus 4 or plus y equal to 2, this is going to be a lot more challenging in this situation to get y explicitly by itself and write a function in terms of just x. And so this is where the need really comes up for being able to have this implicit differentiation, because as we progress in our mathematical careers, it's not always going to be feasible to write an equation explicitly. And so we need some way to be able to take the derivative of a function that's not written explicitly. So that's where implicit differentiation comes about. And what we're going to use is all of our rules, the big three. We have a product rule, the chain rule, and the quotient rule are all intertwined with implicit differentiation. So it's not like a what do I use when? It's more like looking at your situation and saying, is this an implicitly defined function? If it is, and then as you go through, go, okay, I have a product here. Do I also have a chain rule going on? It's not going to be a one size fits all. We're going to potentially have to use all of these different rules within one type of problem. So just keep that in the back of your head as you're always looking for opportunities where you might need to use the product rule or the quotient rule or the chain rule. And our implicit differentiation is really going to apply when we have the situation where x and y are on the same side. So let's take a look. Currently, we've been having situations like this, x cubed. And when we take the derivative, we say we're taking the derivative with respect to x. So notice when we take the derivative, this dx has an x variable, and this is in terms of x. So we're cool. When we do this, we get 3x squared, right? We use that power rule there. And that's awesome. But when I now do the same type of thing, so I take the derivative with respect to x, but my expression has a y in it, now I have an issue because this x, although it matches this x right here, it doesn't match this y. So what we need to do is we need to take the derivative of this implicitly. So I'm going to go ahead right here. And actually, let's back up a second. Let me get rid of this x, simplify it down a little bit. So we're doing d dx of just y cubed first. And so notice this x and this y don't match. So what we're going to do is we're going to use our chain rule. We're going to say, all right, well, I know that y is a function of x. And so I know that somewhere in this function y, there is an x variable. I just don't know what it is. So we're going to start by taking the derivative of the outside of my function. My outside function is y cubed. So I'm going to take the derivative of that. I'm going to say I have 3y squared. And just like with the chain rule, I'm going to multiply it by the derivative of the inside. The only problem is I don't know what that y function is. So I'm going to have to write that as dy dx. And this says that I'm taking the derivative of the outside function. So the derivative of y cubed, again, is 3y squared times the derivative of the inside function. My inside function is y. And I'm taking the derivative of that with respect to x because I'm assuming that within that y function, there's some x variable that I can take the derivative of with respect to that. So this would be my solution. And actually, if we jump back a little bit, let's look at an example like y equals 4x. We've actually been doing this all along, and this is where this notation comes from. If I were to take the derivative of this, what I'm really doing is taking the derivative of both sides. We just didn't write it like that before because we didn't have this chain rule idea of taking a derivative of a composite. So when I take the derivative of y with respect to x, I get dy dx. Because the derivative of y is 1, and the derivative of the inside function is dy dx, and multiply it. So it's really like 1 times dy dx, which we just write as dy dx. And then the derivative of 4x with respect to x is just 4. So we've actually been doing this all along, writing out this notation. If we're using that dy dx notation, we just couldn't really fully understand it yet. And so waited until now to explain where this notation came from. And again, this dy dx is the same as writing y prime equals 4. So those mean the exact same thing. All right, let's take a look at that other example. So let's look at taking the derivative with respect to x of xy cubed. So you'll notice here that we have a product between our x and our y. And what I like to do when I analyze this before I take the derivative is if there's a product, I go ahead and I put that little multiplication sign in there, just so that I don't forget to use my product rule. So I'm going to come off on the side and say, okay, this is f and this is g. So the derivative, or rather, f is equal to x, f prime is equal to 1. G is equal to y cubed. Again, I'm taking the derivative with respect to x. So g prime, we did this over here, is going to be 3y squared dy dx. And then I just follow my product rule. So it's the derivative of f, which is 1, times g, which is y cubed, plus the derivative of g, which is 3y squared times dy dx, multiplied by f, which is x. So what I end with is y cubed plus 3xy squared times dy dx. All right, let's look at some more examples. Let's say we are taking the derivative with respect to x of x plus 3y. So we're going to take it step by step. The derivative with respect to x of x is just 1. The derivative with respect to x of 3y is going to be the derivative of what 3y is, which would just be 3, times the derivative of the inside of this function, which is dy dx. Let's do one more. So we have the derivative, we're taking the derivative with respect to x of x squared, subtract 2y cubed plus 4y, subtract 2. The derivative with respect to x of x squared is just 2x because, again, this x matches that. Now these don't match. So I do subtract. I take the derivative as if I were taking the derivative with respect to y. So I say, okay, well, that's going to be 6y squared. But then I need to take the derivative of the inside of this y function, which we represent by writing dy dx. Plus, again, this has a y, so it's going to be the derivative of this function 4y with respect to y, which is just 4, times dy dx. And then the derivative of 2 is 0, so it goes away. All right. Let's take a look now at kind of an application of this. So we have here a circle in the coordinate plane. And the first thing we're going to do is figure out what the equation of this circle is. So we're going to go ahead and try to find the center of this circle. And we see that it's going to be pretty evenly split. So let's just go ahead and try to find that center first. So we're at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're good. That's 3 and 2. 3 to 8 is 5. So our center right here is at 3, negative 2. And our radius of this circle is 5. So if we're writing the equation of this circle, it follows the form x subtract h all squared plus y subtract k all squared equal to r squared. And so we have x subtract 3 all squared plus y plus 2 squared equals 25. Now we need to be able to figure out, we need to take the derivative of this function to be able to figure out the slope of the tangent line at any point on here. So let's go ahead and take the derivative of this with respect to x. All right, so I'm going to start with this term. This term is in terms of x, so that's great. We're just going to go ahead and use our chain rule. We bump the 2 to the front. We multiply it by x subtract 3, and then the derivative of the inside here, which is just 1, plus, now this has a y, so we're going to use our chain rule because we're going to take the derivative of this whole function. So that gives me 2 times y plus 2. Then you take the derivative of the inside of this, which is just 1, so we're cool. And then I need to take the derivative of the inside of just this function, which is going to be times dy dx. And the derivative of 25 is 0. And now in order to find the derivative, now that I have an equation, I need to actually solve for dy dx. So I'm going to go ahead and I'm going to multiply, I'm going to subtract this whole expression over to the other side, because I can keep things grouped quite nicely here. So I'm left with 2 times y plus 2 equal to a negative 2 times x subtract 3. Oops, I dropped the dy dx. All right, then I'm going to divide by this whole expression. So we end up with negative 2 times x subtract 3 over 2 times y plus 2. My 2's cancel. And so I'm actually left with the dy dx equal to negative x subtract 3 over y plus 2. So this provides the derivative for any point on that circle. Now let's say we have this point right here at 6, negative 6. That would give me 3 squared, which is 9. 8 squared is 8. Got 9 plus 16 equals 25, so that's definitely a point on my circle, 6, negative 6. All right, and so let's say I want to figure out what the slope is of this tangent line right here that passes through the point 6, negative 6. All I would have to do here is say, all right, I'm finding dy dx, which is equal to negative x subtract 3 over y plus 2, and I'm evaluating it at the point 6, negative 6. So notice I can no longer, now that we have this implicit differentiation, this derivative depends on both x and y. So I can no longer just sub in x, I need to know what the corresponding y value is. So I'm going to go ahead and sub that in, put it down here so I have some space, and I get a negative 6 subtract 3 over a negative 6 plus 2. So I have a negative 3 over a negative 4, which is a positive 3/4, which matches very well with what I seem to have here for the slope of that line. All right. Let's try out these examples. So we're taking the derivative with respect to x in each of these examples. So again, I'm going to start by taking the derivative of y squared. That gives me 2y, and then because these don't match, I have to multiply by dy dx. Derivative of 2x is simply 2, plus the derivative of 3y will be 3 times dy dx. And now this is where our algebra skills really get a good workout. I need to figure out what dy dx is. So in order to do that, I want to get all my dy dx's to the same side, and then any term that doesn't have a dy dx, I want to get that to the other side. So I'm going to go ahead and subtract 3 dy dx to the other side. And I now have 2y dy dx, subtract 3 dy dx equal to 2. I'm going to go ahead and factor out this dy dx. So I'm going to bring that to the front. It's like the reverse distributive property. We're taking out the greatest common factor. So again, I factored out that dy dx, I brought it to the front. Notice I could redistribute this and it would look just like this expression. And now I want to get this by itself. These two are attached by multiplication, so I'm going to divide by this whole expression. So I end up finding out that my derivative is equal to 2 over 2y subtract 3. Let's try this one. We're taking the derivative with respect to x. So we get 2 plus e to the y, because the derivative of e to the y is e to the y. But since this y doesn't match that x, I need to multiply by dy dx equals 2x subtract 2y dy dx. I'm going to get all my dy dx terms to one side and all my terms that don't have dy dx to one side. So I need to add this 2y dy dx over to this side. And I need to subtract this 2, do it in a different color. I'm going to subtract this 2 over to the other side. So what I end up with is 2y dy dx plus e to the y dy dx equal to 2x subtract 2. I'm going to factor out my dy dx's. And then I'm going to divide by 2y plus e to the y. So I end up with dy dx equals 2x subtract 2 all over 2y plus e to the y. All right. Let's do these last two problems. Taking the derivative with respect to x again. I notice that I have a product rule here. I'm going to group this 2 with the x just to make it a little bit easier. So I'm multiplying, letting f be 2x and g be y. So I'm going to write that over here. F equals 2x. So f prime is 2. G is y, which means g prime. The derivative of y with respect to y is 1 multiplied by dy dx. So it's just going to be dy dx. So I'm going to go ahead and do this out. I have f prime, which is 2 times g, so y, plus g prime, which is dy dx, times f, so I'm going to write that as 2x times dy dx, equals, this is going to be 6y dy dx, plus 2. Again, I need to group these together, and I need to group those together. So I'm going to bring this over to the other side. I'm going to bring that over there. So I have 2x dy dx, subtract 6y dy dx, equals 2 subtract 2y. I'm going to factor out this dy dx. And I'm going to divide by 2x subtract 6y. So I end up with dy dx equal to 2 subtract 2y all over 2x subtract 6y. All right, last one. Taking the derivative with respect to x, we get 15x squared, derivative of 3 is 0, equals 2 dy dx. And now I have a product rule. I'm going to group this negative 3x squared together. So I have a negative 6xy plus derivative of y is just going to be a negative 3x squared times dy dx, because the derivative of y will just be dy dx, because it's 1 times dy dx. So I need to group these two together. They're already on the same side, which is nice. So I just need to bring that guy over. I have 15x squared plus 6xy equals 2 dy dx, subtract 3x squared dy dx. And now I factor out that dy dx. And go ahead and divide. So we end up with dy dx equal to 15x squared plus 6xy all over 2 subtract 3x squared. All right, these are our practice problems that we're going to take a look at. Here are the solutions. So for this first one, I'm going to take the derivative, and then we're going to find dy dx for each of these. So I'm taking the derivative with respect to x. So I get 6x squared, subtract 2y dy dx, plus 3 dy dx. Oops, sorry, equals 3 dy dx. I'm going to bring that 2y over to the other side. So I get 6x squared equals 3 dy dx plus 2y dy dx. I'm going to factor out that dy dx to be left with 3 plus 2y on the inside. And so my final answer, when I divide by that 3 plus 2y to the other side, is going to be 6x squared over 3 plus 2y. Over here, again, I'm going to take the derivative with respect to x. I get 3x squared, and now I have a product rule. This time, I'm going to group this negative with the x. I'm going to view that as a negative x. So my f is negative x, so my f prime is negative 1. My g is y, which means g prime is dy dx. So I have here the derivative of f prime, which is negative 1 times y, plus g prime, which is dy dx, times a negative x, plus 2y dy dx equals 0. I'm just going to rewrite this. I have 3x squared subtract y subtract x dy dx plus 2y dy dx equal to 0. I'm going to bring these two terms over to the other side, and I'm going to at the same time factor out that dy dx. So I have dy dx, and I'm going to rearrange these a little bit. That's 2y subtract x equals y subtract 3x squared. I'm going to divide by 2y, subtract x. And I have my derivative right here. Just running out of space. All right, notice in this one I have two product rules. This one's a doozy. So I'm going to start off here. I'm going to take the derivative of this first term, which is 2x, and I'm going to multiply it by the second term. Then I'm going to take the derivative of the second term, which is dy dx, and multiply it by the first term. Then I'm going to move on to this one. I'm going to take the derivative of this first term, which is 2y dy dx, multiply it by the second term. Add to that the derivative of this second one, which is 1 times whatever this first one was, y squared, equals 0. So I'm just going to rewrite this so that it makes a little bit more sense. I have 2xy plus x squared dy dx plus, it looks like I have 2, this x needs to bump to the front here. So I have 2xy dy dx plus y squared. And don't underestimate the usefulness of just rewriting things in a neat, organized way, because you have a lot of variables going on here and it's very easy to lose sight of something. So you want to just take that extra step, even though it's taking up an extra line in your notes, to just rewrite things and make sure that they look organized so that you can figure out what your next step is. So now I see that these two terms have the dy dx. So I'm going to bring these terms that don't over to the other side. So I now have dy dx multiplied by x squared plus 2xy. That's equal to, I'm going to bring both of these over to the other side, and negative 2xy subtract y squared. And then I'm going to go ahead and divide. So I'm left with, I'm left with negative 2xy subtract y squared all over x squared plus 2xy. Some people may also write this numerator as a negative 2xy plus y squared. That's totally fine as well. Either way works. And you do always want to check to see if anything cancels out, but generally that's not going to occur. All right, last one. Again, we have the product rule here. So because I'm dealing with trig functions, I'm going to come off to the side here. I'm going to say I have f is 2 sine of x. So f prime is 2 cosine x. And then g is cosine y, which means g prime is going to be a negative sine of y times dy dx. So I have f prime, which is 2 cosine of x times cosine of y, plus g prime, which is a negative sine of y dy dx, times 2 sine of x, equal to 0. I only have one term that has this, but this whole thing is grouped together. So I need to bring, I'm actually going to bring this all the way over to the other side, so that I have, just to make it positive, so I have 2 cosine x cosine y equal to, I'm going to bump this to the front. So I have a 2 sine x sine y dy dx. I'm going to divide. So I end up the 2's are going to cancel, and cosine x over sine x is cotangent. So I have cotangent x, cosine y over sine y is cotangent y. And then I'm done.